Something happened inside a laboratory in Geneva, and nobody fully understands it yet. Not the scientists who designed the experiment, not the physicists who reviewed the data, not the theorists who have spent their entire careers building mathematical models to describe exactly what reality is supposed to do at the smallest possible scales. Something happened. The instruments recorded it faithfully. The numbers came back clean. And what those numbers described was something that the current laws of physics say cannot exist. Not something unlikely. Not something improbable in the way that a coin landing on its edge is improbable. Something that the foundational structure of our entire understanding of the universe says must not, under any circumstances, ever happen. And yet, it did. And that is where we begin. Not at the edges of what is known, but at the edges of what is knowable. At the precise location where the framework we have used to describe everything from the motion of planets to the behavior of atoms has begun, very quietly, very disturbingly, to crack. You already feel it, don't you? There is a particular kind of unease that settles in when something that is supposed to be permanent turns out to be fragile. It is not the unease of danger, not the sharp electric jolt of fear. It is something slower and more unsettling. The creeping recognition that something you were never supposed to question may not deserve the certainty you gave it. Physics is full of these certainties. We teach them to children. We build skyscrapers on them. We launch satellites with them. We design the microchips in the device you are watching this on, using equations that we trust so completely that their reliability is essentially invisible to us, woven into the background of everything we call real. And that invisibility is exactly what makes this moment so strange. Because when you stop noticing the ground beneath your feet, you stop wondering if it might give way. Before anything else, you need to understand what a physical law actually is, because the word law is doing enormous philosophical work here, and most people have never been asked to look at it closely. A physical law is not a rule that was voted on, legislated, or imposed by some authority. It is not even quite a description of what tends to happen. A physical law is a statement of what must happen every single time, without exception, regardless of location, regardless of scale, regardless of what else is occurring in the universe around it. The law of conservation of energy does not merely say that energy is usually preserved. It says that energy is always preserved, that it cannot be created from nothing and cannot vanish into nothing, that every joule of energy that existed at the beginning of any given interaction will still exist, in some form, at the end of it, always, no exceptions. These laws are the skeleton of reality itself, the architecture upon which everything else is constructed. And scientists do not hold them the way people hold opinions. They hold them the way you hold the floor beneath your feet, with the confidence that comes from never having questioned them, because they have never given you reason to. And that confidence was earned. Let's be completely clear about that, because this is not a story about science being wrong. This is a story about something far stranger, something that science itself is struggling to articulate, which is the possibility that the laws we discovered are not the laws of the universe, but the laws of the universe as it happens to be in this particular region, at this particular moment, within a particular set of conditions that we may have mistaken for the conditions of everything. That distinction matters more than almost anything else you will hear in this video, because if the laws of physics are truly universal, then a violation anywhere is a catastrophe everywhere. But if the laws of physics are something more like local habits, patterns that the universe has settled into without necessarily being compelled to stay in them forever, then what we have been witnessing in recent years is not a catastrophe. It is something far more disorienting. It is the universe beginning to show us its other face. To understand why any of this matters, you have to go back to the moment when human beings first decided to trust physics at all. Not the moment a textbook was written, but the actual, psychological moment when the idea that the universe follows rules became genuinely believable. That moment arrived slowly, over centuries, and it arrived with the face of an apple falling from a tree, with the arc of a cannonball, with the orbit of a moon, with the ticking of a pendulum. Isaac Newton looked at these things and saw something that no one had clearly seen before, that the same force pulling an apple toward the ground was pulling the moon toward the earth, that gravity was not a local phenomenon but a universal one, that the same rule applied to everything with mass everywhere without variation. This was staggering. This meant that the universe was not chaotic and arbitrary, not ruled by invisible whims or divine caprice, but mathematical, predictable, lawful, and if it was lawful here, on this small blue rock circling an ordinary star, then it was lawful everywhere, in every galaxy, at every moment in time. That was the promise. That was the covenant that physics made with humanity, and for 300 years it seemed to hold. The trust deepened with every generation. James Clerk Maxwell unified electricity and magnetism into a single framework in the 1860s, and in doing so accidentally predicted the existence of electromagnetic waves, including light, which he had not been looking for. The equations were so precise, so internally consistent, that they could not be wrong about what they implied. Light was an electromagnetic wave, and it moved at a speed that the equations specified exactly, and that speed, it turned out, was constant. Not constant relative to one observer, and slightly different relative to another, the way the speed of a baseball changes depending on whether you are standing still or running. Constant for everyone, always the same. This was deeply counterintuitive, and it took Albert Einstein to take that counterintuitive result seriously enough to follow it all the way to its logical conclusion, which was that if the speed of light is fixed, then time and space must be flexible. That conclusion became the special theory of relativity, and then the general theory, which reframed gravity not as a force but as a curvature of space-time itself, and which was confirmed so precisely and so repeatedly that GPS satellites have to account for relativistic effects on their clocks just to give you accurate directions. The laws held, they kept holding, and with every confirmation, the trust grew deeper. Then came quantum mechanics, and reality took its first strange turn. Not a violation, not yet, but a warning. A hint that the universe at its smallest scales was not merely complicated, but fundamentally different in character from everything that had come before. When Max Planck and then Niels Bohr and then Heisenberg and Schrödinger began to describe the behavior of particles at the atomic scale, what emerged was a picture of reality that was, by every measure of classical intuition, absurd. Electrons did not orbit the nucleus the way planets orbit the sun. They existed in clouds of probability, in superpositions of states, neither here nor there until a measurement was made. Light behaved like a wave when no one was looking at it, and like a particle when someone was. Particles communicated with each other across vast distances instantaneously, a phenomenon Einstein called spooky action at a distance, and which he refused to accept, not because he had a good argument against the math, but because it violated his deepest intuitions about how reality should work. And yet, quantum mechanics was confirmed experimentally, with a precision that bordered on the miraculous. It predicted the behavior of electrons, photons, and atoms to the 15th decimal place. No theory in the history of science has ever been more accurate. And yet, if you sat down with a physicist and asked them to explain, in plain language, what quantum mechanics actually means, what it actually says about the nature of reality, you would find yourself in a conversation that ends in one of several ways, all of which are deeply unsatisfying. This is the first place where the ground begins to feel less solid. Quantum mechanics works. It works extraordinarily well, but physicists do not agree on what it means. There are, at last count, at least a dozen serious, mathematically rigorous interpretations of quantum mechanics, and they make the same predictions about measurements, but describe completely different, underlying realities. In the Copenhagen interpretation, the wave function collapses when a measurement is made, and asking what the particle was doing before the measurement is a category error, a meaningless question. In the many worlds interpretation, the wave function never collapses. Instead, every possible outcome occurs in a separate branch of a constantly branching universal wave function, and you, right now, are one copy of yourself in a cosmos of infinite copies, each living out a different version of every quantum event that has ever occurred. In the pilot wave interpretation, particles have definite positions at all times, but are guided by an invisible wave that is itself not directly observable. These interpretations are not equivalent philosophically. They describe fundamentally different universes, and yet no experiment can currently distinguish between them. This means that quantum mechanics, the most successful scientific theory ever constructed, is at the same time a theory whose meaning is genuinely unknown. We can use it, but we cannot say with any confidence what it is telling us about what is real. That is an extraordinary thing to admit. and it is the foundation on which the rest of this story is built. Now hold that thought about quantum mechanics and bring it alongside what we know about general relativity, because here is where the story takes a turn from the merely philosophically discomforting to the scientifically critical. General relativity and quantum mechanics are both extraordinarily accurate theories. They are the two pillars upon which all of modern physics rests, and they are, at a deep mathematical and conceptual level, incompatible with each other, not disagreeing at the edges, not slightly off in their predictions. Fundamentally, structurally, apparently irreconcilably incompatible. General relativity describes gravity as the smooth, continuous curvature of space-time. Quantum mechanics describes everything else, in terms of discrete, probabilistic interactions between quantized fields. When you try to apply the methods of quantum mechanics to gravity, which should work if both theories are correct, the mathematics produces infinities, literal infinities, not very large numbers that eventually stabilize, but quantities that grow without bound, that cannot be renormalized the way quantum electrodynamics can, that refuse to resolve into anything physically meaningful. The equations break, not metaphorically, literally. The mathematics that physicists use to calculate the behavior of every other fundamental force simply stops functioning when you point it at gravity. And gravity is not a minor player in the universe. It is the force that shapes the structure of everything at the largest scales. The incompatibility between these two theories is not a gap at the edge of physics. It is a chasm running through the center of it. You might be thinking that this is simply a problem waiting to be solved, that someone will eventually come along with a better framework that unifies the two theories and everything will be fine. And you would not be wrong to think that. String theory was proposed partly to fill exactly that gap. Loop quantum gravity was another attempt. There have been many others. But here is what is important to understand. After decades of work, enormous intellectual effort, entire careers devoted to bridging this gap, we do not yet have a confirmed theory of quantum gravity. We have candidates. We have mathematical frameworks that are beautiful and internally consistent and full of remarkable predictions, but we have no experimental confirmation of any of them. String theory predicts the existence of extra spatial dimensions curled up at scales far smaller than we can currently probe. It predicts the existence of supersymmetric partner particles for every known particle in the Standard Model. Decades of searching at the most powerful particle collider ever built have found no evidence of supersymmetry. None. The theory might still be correct. The extra dimensions might exist but be too small to detect with current instruments. But the absence of evidence has begun to feel, to many physicists, like something more than a temporary gap. It has begun to feel like a signal. And then something happened that made this problem feel significantly more urgent. In 1998, two independent teams of astronomers were studying distant supernovae, specifically a type of supernova called Type Io, which is useful to cosmologists because it always explodes with roughly the same intrinsic brightness, making it function as what astronomers call a standard candle, a light source whose true brightness you know, so that you can calculate how far away it is based on how dim it appears from Earth. The two teams were using these standard candles to measure the rate at which the universe had been expanding since the Big Bang, expecting to find that the expansion had been slowing down over time, pulled back by the gravitational attraction of all the matter in the universe. What they found instead was that the expansion was not slowing down. It was speeding up. The universe was accelerating in its expansion, and whatever was driving that acceleration was not accounted for by any known physics. Both teams thought they had made a mistake. They went back through their data. They checked their instruments. They looked for systematic errors. They found none. The data was clean. The universe was accelerating and something was causing it. That something was given the name dark energy, which is a placeholder word, a way of saying, we know something is here, but we have absolutely no idea what it is. Dark energy is now thought to constitute approximately 68% of the total energy content of the universe. 68%. The vast majority of everything that exists in terms of energy is something we cannot detect, cannot characterize, and cannot account for within the framework of our most sophisticated physical theories. Dark energy is not a solved problem that has been given a name. It is an unsolved mystery that has been given a name to make it easier to talk about. And then there is dark matter, which is a different mystery but one that compounds the unease considerably. Dark matter was first proposed in the 1930s by the astronomer Fritz Zwicky, who noticed that galaxies and clusters were moving too fast for the amount of visible matter they contained. At the speeds they were moving, the gravitational pull of all the stars and gas within them should have been insufficient to hold them together. They should have flown apart. They did not. Something was holding them. Something with mass, because only mass generates gravity, but something that emitted no light, reflected no light, and interacted with nothing that we could directly detect. Dark matter. And in the decades since Zwicky's first observation, the evidence has mounted until it is overwhelming. The rotation curves of individual galaxies, the way light bends around galaxy clusters in a pattern consistent with much more mass than is visible, the large-scale structure of the universe, the way galaxies cluster in a cosmic web of filaments and voids, which can only be explained by the gravitational scaffolding of something invisible. All of this points to dark matter. It is everywhere. It constitutes roughly 27% of the universe's total mass energy, and we have never directly detected a single dark matter particle. Decades of incredibly sensitive experiments designed specifically to catch dark matter interacting with ordinary matter have come up empty. Every candidate particle that could have explained it has been ruled out or pushed further and further toward the edges of plausibility. We know it is there. We cannot find it. We cannot say what it is. And without it, our model of the universe does not work. So, let us pause here and count what we have so far, because the accumulation is beginning to matter. We have a quantum mechanics that works perfectly but whose meaning is unknown. We have a general relativity that works perfectly but is mathematically incompatible with quantum mechanics. We have a universe that is 68% dark energy, which is an unknown force driving an accelerating expansion we cannot explain. We have a universe that is 27% dark matter, which is an unknown substance we have never detected. This means that ordinary matter, the stuff made of protons and neutrons and electrons, the stuff of stars, planets, people, and everything we have ever touched or seen or measured, constitutes approximately 5% of the universe's total mass energy content. 5%. Our laws of physics, which we describe as a complete and mature description of reality, were derived entirely from and successfully describe 5% of what exists. The other 95% is operating by rules we do not know, in forms we cannot see, for reasons we cannot currently articulate. If this were any other domain of knowledge, we would say that we know almost nothing about the subject. In physics, we have somehow convinced ourselves that we have a nearly complete picture of reality. That conviction becomes harder to maintain the longer you look directly at those numbers. But let's go deeper, because the problems do not stop at the cosmic scale. They do not even stop at the quantum scale. They exist at the intersection of measurement and reality, at the precise boundary where the observer meets the observed, and that boundary is far stranger and far less stable than you have probably been led to believe. The double-slit experiment is perhaps the most famous and most deeply unsettling experiment in the history of physics, and if you have heard of it before, I want to ask you to hear it again with fresh ears, because most explanations of it understate how profoundly strange it actually is. In the experiment, particles are fired one at a time at a barrier with two narrow slits in it. On the other side of the barrier is a detector screen. When both slits are open and no one is measuring which slit the particle goes through, the particles create an interference pattern on the screen, the kind of pattern that can only be produced by a wave. The particle is behaving like a wave, spreading through both slits simultaneously and interfering with itself. But here is the part that breaks your brain. When a detector is placed at the slits to determine which one the particle actually goes through, the interference pattern disappears. The particle begins to behave like a particle again, going through one slit or the other, not both. The act of observation, the mere introduction of a device that could in principle record which path the particle took, changes the physical outcome of the experiment. Not in a way that makes intuitive sense, not because the detector is physically disturbing the particle with some kind of interaction that we could account for, but in a way that seems to suggest that the particle knows it is being watched. That reality responds to measurement, that the act of looking changes what is there. Now, physicists will tell you that this is well understood, that it is simply a consequence of quantum mechanics, that the wave function collapses upon measurement, and this is all within the framework, and in a narrow technical sense, that is true. But the explanation raises more questions than it answers. What is a measurement? What counts as an observation? Does the measuring device have to be conscious? Does it have to be capable of recording information in a stable way? Does it have to interact with a human nervous system? These questions are not peripheral. They are central to what quantum mechanics means, and there is no consensus on the answers. In one famous experiment, the quantum eraser experiment, researchers demonstrated that the interference pattern can be restored even after the particle has already hit the detector screen by erasing the witch path information that was previously recorded. The outcome of the experiment is apparently altered after it has already occurred, which raises questions about causality so severe that most physicists simply prefer not to think about them too directly. The delayed choice quantum eraser experiment is one of the most disturbing results in the history of physics, and its implications for the structure of time and causality are not fully resolved, not by a long stretch. Speaking of time, of all the concepts in physics, time is perhaps the one that is most taken for granted and most poorly understood simultaneously. You experience time as something that flows, that moves in one direction, from past to present to future, with an arrow that is clear and obvious, and apparently absolute. But here is what the physics actually says. The fundamental equations of physics are, with a very small number of exceptions, time-symmetric. They work just as well if you run them backward. A video of two billiard balls colliding and bouncing off each other is indistinguishable from that same video played in reverse. Newtonian mechanics does not have a preferred direction of time built into it. General relativity does not have a preferred direction of time built into it. Even quantum mechanics, at the level of its fundamental equations, is largely time-symmetric. The arrow of time, the deep sense you have that the past is fixed and the future is open, that events happen in a specific sequence and cannot be undone, does not come from the fundamental laws of physics. It comes from something else. Most physicists believe it comes from the concept of entropy, from the second law of thermodynamics, which says that systems tend to evolve from ordered states to disordered states, that the entropy of a closed system tends to increase over time, and in a statistical sense, this gives us the arrow of time. The universe started in an extremely low entropy state just after the Big Bang, and it has been moving toward higher entropy ever since. And that gradient, that movement from order to disorder, is apparently what creates the experience of time moving forward. But this explanation, satisfying as it may seem, immediately raises a deeper question. Why did the universe start in such an incredibly low entropy state? Why was the Big Bang so extraordinarily ordered? And that question currently has no good answer, which means that the arrow of time, one of the most fundamental features of your experience of reality, is grounded in something that physics cannot currently explain. And if time is not what it appears to be, then causality, which is built on time, is also not quite what it appears to be. Causality is the principle that cause must precede effect, that the past influences the future and not the other way around. It is so deeply embedded in our intuitive understanding of reality that it feels like a category of thought rather than a contingent fact. But causality has been violated experimentally, not in ways that allow you to send a message backward in time, not in ways that produce paradoxes in the Hollywood sense, but in ways that are genuinely incompatible with a naive reading of causality as something fundamental and inviolable. When two particles become quantum entangled and then separated by a large distance, measuring one particle instantaneously determines the state of the other, regardless of the distance between them. This correlation cannot be used to send information faster than light, due to the statistical nature of quantum measurements, so it does not violate special relativity in the strict sense. But the correlation itself is real, verified by Bell test experiments with increasing precision and ever-shrinking loopholes, and it implies that something connects the two particles in a way that is independent of the spatial distance between them. That something is not a force, it is not a signal, it is not any known physical mechanism. It is a connection that exists outside the usual framework of space and time. And when a team of physicists at the University of Vienna performed a variant of the Bell test in space, using a satellite to send entangled photons to two ground stations separated by over 1,000 kilometers, the correlations held. Space did not weaken them, distance did not attenuate them. The connection was as strong across 1,000 kilometers as it would be across a tabletop. Whatever is causing this, It is not operating according to the laws of locality that classical physics assumed to be fundamental. Let's talk about the Hubble tension, because it is one of the most concrete and most recent indications that something is genuinely wrong with our understanding of the universe. And unlike the more philosophical puzzles we have been discussing, this one shows up as a number, a specific, measurable, precisely quantified disagreement between two different methods of measuring the same thing, and the disagreement is stubbornly, persistently, disturbingly real. The Hubble constant is a measurement of how fast the universe is expanding, expressed as a velocity per unit of distance. There are two primary ways to measure it. The first uses the cosmic microwave background, the faint afterglow of the Big Bang, which fills all of space with microwave radiation, and carries within it an imprint of the early universe's density fluctuations. By fitting a model to this data, the Planck collaboration has derived a value for the Hubble constant of approximately 67.4 kilometers per second per megaparsec. The second method uses the cosmic distance ladder, measuring the distances to nearby galaxies using Cepheid variable stars and type Ia supernovae, and then inferring the expansion rate directly from observed redshifts. This method, refined over many years by teams including the SUS collaboration, consistently gives a value of approximately 73 kilometers per second per megaparsec. These two numbers, 67.4 and 73, seem close, but in physics, the difference between them, given the precision of both measurements, represents a statistical tension of roughly 5 standard deviations, 5 sigma. In physics, 5 sigma is the threshold for claiming a discovery. Both measurements are now so precise and so carefully vetted that the probability that the discrepancy is a statistical fluke is essentially negligible. Either one or both methods contain systematic errors that neither team has been able to identify, or the standard model of cosmology is wrong, or there is new physics that our current framework cannot account for. Every year, the precision of both measurements increases. Every year, the discrepancy fails to go away. Every year, the list of possible conventional explanations shrinks. The Hubble tension is not a minor technical problem. It is a crack in the foundation of modern cosmology, and it has been widening for over a decade. And the Hubble tension is not alone. There is also what is called the S8 tension, which is a discrepancy between the predicted and observed clustering of matter in the universe. The standard model of cosmology predicts, based on the early universe data from the cosmic microwave background, how strongly matter should be clumped together today. Surveys of the large-scale structure of the universe, measuring the distribution of galaxies and galaxy clusters across vast regions of space, consistently find that matter is somewhat less clumped than the standard model predicts. The discrepancy is smaller than the Hubble tension and less statistically significant, but it is real and it points in the same direction. Something about our model of how the universe evolves is not quite right. There is a pattern beginning to emerge here. A pattern of the universe behaving slightly differently than our best theories say it should, not dramatically, not in ways that are immediately obvious, but persistently, reproducibly, in multiple independent measurements using different instruments and different methods. When a single anomaly appears in science, it is reasonable to suspect an error. When multiple anomalies appear simultaneously, pointing in similar directions at the most fundamental levels of our description of the universe, that begins to feel like something else. It begins to feel like evidence. Now step back and look at what the scientific community's response to all of this has been, because it is illuminating in a way that is both admirable and slightly unnerving. The response has been, in the main, to search for new physics within the existing framework, to propose modifications to the standard model that are as minimal as possible, while being sufficient to explain the anomalies. Physicists have proposed modified gravity theories that tweak the behavior of general relativity at large scales to explain dark energy without requiring a cosmological constant. They have proposed self-interacting dark matter, warm dark matter, fuzzy dark matter that decays, dark matter that has its own force carriers, all in an attempt to explain the structure of galaxies without changing the fundamental framework. They have proposed early dark energy, interacting dark energy, decaying dark energy, phantom dark energy, as ways to resolve the Hubble tension while keeping the standard model intact. All of these proposals are serious scientific hypotheses. Many of them are mathematically rigorous, and so far, None of them have provided a fully satisfying explanation of all the anomalies simultaneously. Each solution tends to resolve one tension while making another worse. The framework is not yielding gracefully to modification. It is resisting, and the resistance is informative. Let's go even deeper now, because there is a level of the story that is rarely told clearly, that lives beneath the anomalies and the tensions and the incompatible theories, and it has to do with the nature of the scientific enterprise itself, with the philosophy of what we are doing when we do physics. Physics is built on measurement. Every claim that physics makes about the world is ultimately grounded in an act of measurement, in a number produced by an instrument, a detector, a telescope, a collider. And here is the thing about measurement that is easy to miss. It is always indirect, always. You never directly perceive an electron. You never directly see a galaxy. You see traces, tracks in a detector medium, points of light on a photographic plate, voltages in a photodetector, ripples in the arms of a laser interferometer, the electron, the galaxy, the gravitational wave, the particle. All of these things are inferences, models we build to explain what our instruments tell us, and the models we build are shaped by the assumptions we bring to the data. This is not a critique of physics. It is a description of how all knowledge works. But it has an important implication. If the assumptions we bring to our measurements are subtly wrong, the models we build will be subtly wrong in ways that may be very difficult to detect, because we are using those same assumptions to check whether our models are correct. This is not a hypothetical concern. It has happened before. For much of the 19th century, physicists worked within a framework that assumed the existence of the luminiferous ether, an invisible medium that filled all of space and through which light traveled as a wave, the way sound travels through air. This assumption was not a casual guess. It was deeply embedded in the conceptual framework of the time, supported by analogy with every other known wave, and assumed to be physically necessary. The Michelson-Morley experiment of 1887, designed to detect the Earth's motion through this ether, found nothing. No ether wind. No variation in the speed of light depending on direction. The experiment was repeated, refined, modified. Nothing. The ether did not exist. And yet, it took decades and the conceptual revolution of special relativity to fully remove it from the framework. The lesson of the ether is not that scientists are foolish. The scientists who believed in the ether were among the smartest and most rigorous people in human history. The lesson is that our deepest conceptual commitments are often invisible to us exactly because they are the lens through which we see everything else. We cannot easily question the assumptions that make our questions possible. So what are the invisible assumptions in contemporary physics? This is a question that is genuinely difficult to answer, for exactly the reasons just described. But there are some candidates. One of the deepest is the assumption of locality, the principle that objects are only directly influenced by their immediate surroundings, that there are no instantaneous connections across space. Quantum entanglement challenges this assumption, as we have discussed, and the challenge has been confirmed with increasingly stringent experiments. Another deep assumption is the assumption of reductionism, the principle that the behavior of a complex system can always in principle be explained by the behavior of its components. Reductionism has been enormously productive, but there is growing evidence that certain phenomena, certain kinds of complexity, exhibit what are called emergent properties that cannot be straightforwardly derived from the properties of their parts. Consciousness may be one example. The behavior of strongly correlated quantum systems may be another. A third deep assumption is what physicists call naturalness, the intuition that the parameters of physical theories should not require extreme fine-tuning to produce the universe we observe. The cosmological constant, the value of dark energy, must be fine-tuned to an extraordinary degree of precision to produce a universe where structure can form. The mass of the Higgs boson requires similarly extreme fine-tuning. These fine-tuned values are not forbidden by any law of physics, but they feel deeply unnatural in a way that physicists have historically taken as a signal that something important is missing from the theory. The failure of supersymmetry to show up at the LHC has left this fine-tuning problem without its most popular proposed solution, and the problem has not gone away. Here is where things become genuinely vertiginous. The fine-tuning of the cosmological constant is not a small fine-tuning. Quantum field theory, the theoretical framework that underlies the standard model of particle physics, predicts that the vacuum of space should contain an enormous energy density due to quantum fluctuations, the constant churning of virtual particles popping in and out of existence at the smallest scales. The prediction for this vacuum energy is a specific number. The observed value of the cosmological constant, the actual energy density of empty space that is causing the universe to accelerate, is also a specific number. The ratio between these two numbers is approximately 10 to the power of 120. The theoretical prediction is off from the observed value by a factor of 10 to the power of 120. This is the largest discrepancy between a theoretical prediction and an experimental observation in the entire history of science. It is not a small error. It is an error so enormous that it suggests one of two things. Either our quantum field theory calculation is catastrophically, fundamentally wrong, or something is canceling out almost all of the predicted vacuum energy with a precision of 120 decimal places, which is a fine-tuning so extreme that it seems to demand an explanation that we do not have. This problem is called the cosmological constant problem, and it has been called by some physicists the greatest unsolved problem in physics. Steven Weinberg, one of the architects of the Standard Model, received the Nobel Prize for his work on electroweak unification, and he has described the cosmological constant problem as one of the deepest mysteries in all of physics. It has been sitting there, unresolved, for decades, and it is not getting smaller. Let's pause for a moment and consider what it would mean if the laws of physics were not universal. Not wrong, exactly, but not universal in the way we have assumed. The philosopher Nick Bostrom and others have pointed out that if you change the constants of nature, even slightly, the universe becomes uninhabitable. If the strength of the electromagnetic force were slightly different, atoms could not form. If the gravitational constant were slightly different, stars could not ignite. If the cosmological constant were any larger than it is, the universe would have expanded so rapidly that matter could never have clumped into galaxies at all. These facts, which are sometimes called the fine-tuning of the universe for life, are not in dispute. The universe's physical parameters sit in a narrow range of values that permit complexity, stars, planets, chemistry, biology. Outside that range, in a vast surrounding space of possible values, the universe would be sterile. The question is, what does this mean? There are three broad answers that physicists and philosophers have given. The first is that the constants are fixed by some deeper theory that we have not yet discovered, that they are not arbitrary but necessary. The second is that there is an enormous number of universes, a multiverse, with different constants in each one, and we are living in the one that happens to be compatible with our existence because in any other one, we would not exist to notice. The third is that we have simply been extraordinarily lucky, and luck, while mathematically permitted, seems like an insufficient answer to a question this deep. None of these answers is fully satisfying. None of them is experimentally confirmed, and each of them carries implications for the nature of physical law that are difficult to process. The multiverse hypothesis deserves a moment of its own attention, not because it is confirmed, it emphatically is not, but because it represents a fascinating and uncomfortable case where physics, in attempting to explain the fine-tuning of constants, has generated a framework that may be fundamentally untestable. If there are an infinite number of universes, each with different physical constants, then the fact that we live in a universe compatible with life is not surprising. It is guaranteed by the logic of selection. But a theory that is compatible with literally any observation is not a scientific theory in the traditional sense. The predictive power that makes science science comes from the ability to specify in advance what you would and would not expect to find. A theory that says anything could happen in this universe because other universes with different constants exist cannot be falsified, and an unfalsifiable theory occupies an uncomfortable middle ground between physics and metaphysics. Some of the most eminent physicists alive today, including Stephen Hawking before his death and Leonard Susskind and Max Tegmark, have seriously embraced versions of the multiverse hypothesis. Others, including Peter Woit and Lee Smolin, have argued that this represents a departure from the scientific method, a willingness to accept explanations that cannot in principle be tested. The fact that this argument is happening at the highest levels of the field, among people who have spent their entire careers doing rigorous mathematical physics, tells you something important. It tells you that the crisis is real, that it is not a pop science exaggeration, and that the people closest to the problem are not in agreement about where the boundaries of legitimate scientific inquiry even lie. And then there is the question of what happens at the edge of a black hole, because black holes are where general relativity and quantum mechanics collide most violently, and the collision produces results that are, depending on your perspective, either deeply fascinating or deeply alarming. A black hole is a region of space-time where gravity has become so extreme that nothing, not matter, not light, not any known signal, can escape from within a certain boundary called the event horizon. General relativity predicts the existence of black holes with complete mathematical precision. It also predicts that at the center of every black hole there is a singularity, a point where the density of matter becomes infinite, where the curvature of space-time becomes infinite, where the equations of general relativity simply break down and produce nonsense. A singularity is not a physical object. It is a mathematical signal that your theory has reached the edge of its own applicability, that you are trying to use it in a regime where it cannot be trusted. General relativity itself contains within it the prediction of its own failure, and when you try to apply quantum mechanics to the interior of a black hole, things do not get better, they get stranger. Stephen Hawking showed in 1974, using a calculation that combined elements of both general relativity and quantum mechanics, that black holes are not perfectly black. They radiate. The quantum fluctuations of the vacuum, the constant churning of virtual particle pairs that pop into and out of existence throughout all of space, can, at the event horizon of a black hole, result in one particle of a pair falling in while the other escapes. The escaping particle carries energy, and over time this process, called Hawking radiation, causes the black hole to slowly lose mass and eventually evaporate entirely. This was a stunning theoretical result, one of the most beautiful and productive syntheses of relativity and quantum theory ever achieved, but it immediately generated a problem so severe that it has been called the black hole information paradox, and it is one of the most contentious and unresolved debates in all of theoretical physics. The problem is this: quantum mechanics requires that information is never destroyed. This is not a minor technical requirement. It is a fundamental axiom of quantum mechanics, a consequence of the unitarity of quantum evolution, which is the mathematical requirement that probabilities always sum to 1. If you know the quantum state of a system at any given time, unitarity guarantees that you can, in principle, reconstruct the state at any earlier or later time. Information is conserved. But Hawking's calculation suggested that the radiation emitted by an evaporating black hole is perfectly thermal, essentially random, carrying no information about what fell in. If that is true, and if the black hole eventually evaporates completely, then all the quantum information about everything that ever fell into the black hole is simply gone, destroyed, which quantum mechanics says is impossible. This is not a minor paradox. It is a fundamental conflict between two of the most successful theories in the history of science. Either quantum mechanics is wrong, which would be catastrophic, or Hawking's calculation is wrong, which would mean that black hole evaporation does not produce perfectly thermal radiation, which would mean there is something subtle and unknown happening at the event horizon that we do not understand. For decades, most physicists assumed that Hawking's calculation must be approximately correct, and that the information paradox would be resolved by some subtle quantum gravitational effect near the horizon. Then in 2012, a group of physicists led by Ahmed Almheri published a paper showing that if information does escape from black holes through subtle correlations in the Hawking radiation, then the event horizon must be dramatically different from what general relativity predicts. Specifically, they showed that the combination of unitarity, locality, and the equivalence principle, which is the foundational assumption of general relativity, is mathematically inconsistent when applied to black hole evaporation. One of these three things must be false. You have to give up unitarity, which means quantum mechanics is wrong, or you have to give up locality, which means information can travel instantaneously, or you have to give up the equivalence principle, which means general relativity is wrong in a much more fundamental way than previously thought. The paper proposed that instead of falling smoothly through an event horizon, as general relativity predicts, an infalling observer would encounter a firewall, a wall of high-energy radiation that would incinerate them before they could cross. If this is correct, then the smooth, featureless event horizon of general relativity is an illusion. The two theories are not merely incompatible in extreme regimes. They are producing mutually contradictory physical predictions about something as concrete as what an astronaut would experience falling into a black hole. The firewall paradox has not been resolved. The debate it sparked is ongoing and has generated an enormous body of work exploring the nature of space-time at the quantum level, including fascinating connections between the geometry of space-time and quantum entanglement, work suggesting that space itself may be built from quantum information, that the geometry of the universe may be an emergent consequence of the way quantum systems share information with each other. This idea, associated with the work of Juan Maldacena and others on the ADS-CFT correspondence, is one of the most remarkable and counterintuitive developments in theoretical physics in the past 30 years. It suggests that a theory of gravity in a higher dimensional space is mathematically equivalent to a quantum field theory, with no gravity living on the lower dimensional boundary of that space. The gravity is holographic, encoded in the boundary theory the way a three-dimensional image is encoded on a two-dimensional hologram. If this is right, then space and gravity are not fundamental. They are derived. They emerge from something else, from quantum information, from entanglement, from structures that are themselves not spatial at all. The universe you see, feel, and navigate through may be a kind of projection, a macroscopic pattern that emerges from a deeper level of reality that does not have the properties of space and time at all. This is not science fiction. It is a serious hypothesis being pursued by some of the most technically sophisticated physicists in the world, and it means that the space you are currently sitting in may not be what you think it is. Let's pull back from the theoretical for a moment and look at something concrete and experimental, because there have been specific moments in recent history where measurements have returned results that should not be possible within the current framework, and these moments deserve to be examined carefully and with full seriousness. In 2021, the muon G-2 experiment at Fermilab returned results showing that the muon, a heavier cousin of the electron, has a magnetic moment that is slightly but measurably larger than the standard model predicts. The discrepancy is small in absolute terms, but it is precise. The experiment is extraordinarily sensitive, using a storage ring the size of a building to measure the precession of muon spins in a magnetic field to a precision of parts per billion. The result, confirmed by previous measurements at Brookhaven National Laboratory, represents a tension with the standard model of approximately 4.2 standard deviations, just below the 5 sigma threshold for discovery, but deeply significant. Something is interacting with muons that the standard model does not account for. Some unknown particle, some unknown force, some physics beyond the standard model is apparently real and apparently measurable, and it is sitting just at the edge of our ability to characterize it, tantalizing and maddening. And there is more. In the same year, 2021, the LHCb experiment at CERN released results from an analysis of particle decays that showed an apparent violation of a principle called lepton universality. In the standard model, the three families of leptons, electrons, muons, and tau particles are treated identically by the weak and electromagnetic forces, except for differences in mass. They should therefore be produced in equal numbers in processes that have enough energy to create any of them. The LHCb experiment found that in certain B-meson decays, electrons and muons were being produced at slightly different rates. If true, this would be a direct violation of lepton universality, which is one of the core symmetries of the standard model. The result had a significance of about 3.1 sigma, not enough for a discovery claim, but enough to generate substantial excitement. Unfortunately, a more refined analysis published in 2022 reduced this significance significantly, suggesting that the earlier result may have been affected by systematic errors. But the fact that the result appeared, was taken seriously, and required enormous refinement to understand illustrates how close physics is currently operating to its own limits of measurement and interpretation. The signal and the noise are uncomfortably close together, but let's stay with the muon G-2 result for a moment longer, because there is a further complication that arrived in 2023 and made the situation simultaneously clearer and more confusing. A new theoretical calculation of the expected muon magnetic moment using a method called lattice quantum chromodynamics which simulates the behavior of the strong nuclear force on a computational grid, returned a predicted value that was significantly different from previous theoretical calculations and much closer to the experimental measurement. If this new calculation is correct, then the tension between experiment and theory largely disappears, and there is no anomaly at all. But here is the problem. The new lattice QCD calculation is itself in tension with other theoretical calculations and with other experimental data, specifically with precision measurements of the electron-positron collision cross-section known as the R ratio. You cannot have both the new theoretical prediction and the experimental data that the old prediction was consistent with. Something, somewhere in the theoretical framework, is inconsistent. You can choose which inconsistency you prefer, but you cannot eliminate them all at once. The anomaly may have moved rather than disappeared, shifting from the comparison between theory and the muon G-2 experiment to a tension within the theoretical framework itself. Either way, something does not fit, and the fact that changing the theoretical calculation to match one experiment immediately creates a conflict with another experiment suggests that the framework is under stress in ways that are not easily localized or resolved. Now let's go somewhere truly strange. Let's talk about the measurement of the proton charge radius, which seems like it should be a simple and settled question, but turned out to be one of the most bewildering puzzles in recent physics. The proton is one of the most studied objects in the universe. It is the nucleus of the hydrogen atom. It makes up most of the visible matter in the cosmos, and its size, specifically the radius of its charge distribution, has been measured many times with considerable precision. For decades, measurements of the proton charge radius using ordinary hydrogen spectroscopy, the study of the light emitted by hydrogen atoms, gave consistent results clustering around a value of about 0.88 femtometers. Then in 2010, a group at the Paul Scherrer Institute in Switzerland measured the proton radius using muonic hydrogen, a hydrogen atom in which the electron has been replaced by a muon. Because the muon is about 200 times heavier than the electron, it orbits much closer to the proton, making it a far more sensitive probe of the proton size. The measurement returned a value of approximately 0.84 femtometers. This is 4% smaller than the value obtained from ordinary hydrogen. 4%. In the world of precision measurement, where the measurements themselves are accurate to a fraction of a percent, a 4% discrepancy is not a rounding error. It is a catastrophe. It was called the proton radius puzzle, and it persisted for nearly a decade, with physicists proposing all manner of exotic explanations, including the possibility of new forces that couple differently to muons than to electrons, which would by itself be a violation of lepton universality. The puzzle was eventually largely resolved by a revised analysis of the ordinary hydrogen data, which shifted the ordinary hydrogen result closer to the muonic hydrogen result. But the episode is instructive, because it shows how a measurement discrepancy can persist for years, generate hundreds of papers proposing new physics, and then turn out to be the result of subtle errors in data analysis, rather than genuinely new phenomena. It also shows how difficult it is to tell the difference between a real anomaly and a systematic error before the situation is fully resolved, and it raises the uncomfortable question of how many other apparent agreements in physics are based on measurements that contain similar undetected systematic errors. This brings us to a question that is rarely asked publicly, but is discussed seriously in the philosophy of science community, and increasingly in physics itself. How would we know if the laws of physics were changing? Not suddenly, dramatically changing in a way that would be immediately obvious, but slowly, subtly, at the edges of our precision, in ways that would look like measurement errors or model uncertainties until enough data accumulated to make the trend undeniable. There is actual evidence that some physical constants may not be constant. Observations of quasar absorption spectra, the patterns of light absorbed by gas clouds between distant quasars and Earth, have been used to measure the value of the fine structure constant, a dimensionless number that governs the strength of the electromagnetic force at different points in the history of the universe. The fine structure constant is one of the most precisely measured quantities in all of physics, known to better than 1 part in a billion here and now. But some analyses of quasar spectra have suggested that its value may be slightly different in different regions of the universe and at different points in cosmic history. The results are controversial and disputed, with other analyses finding no variation. The experimental uncertainties are very large and very difficult to characterize, but the question itself, whether the constants of nature are truly constant, is a legitimate scientific question that is being actively investigated, and if the answer were yes, even slightly, then the laws of physics we have derived from measurements made here and now are not universal laws. They are local snapshots of a reality that is, on scales and timescales we cannot easily access, more variable than we assumed. The variability of the constants of nature is not a new idea. Paul Dirac, one of the founding figures of quantum mechanics, noticed in 1937 that several ratios of fundamental constants were roughly equal to the ratio of the size of the observable universe to the size of a proton, a number of around 10 to the power of 40. He found this coincidence too striking to be accidental and proposed that it might reflect a deeper connection, that the gravitational constant might be inversely proportional to the age of the universe, changing over cosmic time. This idea, known as Dirac's large numbers hypothesis, would imply that gravity was stronger in the early universe. It has been tested and largely disfavored by subsequent observations, but the impulse behind it was scientifically legitimate. The coincidence of the large numbers is real, and the question of why the constants have the values they do remains unanswered. Modern string theory, in a sense, gives a framework in which the constants of nature could in principle take different values in different regions of what is called the string theory landscape, an enormous space of possible vacuum states, each with different low-energy physics. In this picture, the constants are not fundamental but contingent, determined by which region of the landscape our universe happens to occupy, and there is no deeper reason for their values other than the fact that we are here to observe them. If this is right, then asking why the speed of light is what it is, or why the electron has the mass it does, is like asking why the Earth is at the distance from the Sun that it is. The answer is not a deep physical law, but a selection effect. We exist here because here is the kind of place where beings like us can exist. But if the constants are contingent, if they could in principle have been different, then the laws that depend on them are also contingent. And if the laws are contingent, then physics is not the discovery of necessary truths about the structure of reality. It is the mapping of one particular instance of a universe from a much larger possibility space of universes, most of which we will never observe. This is not a comfortable conclusion. It strips physics of a certain kind of metaphysical authority. It transforms the laws of physics from eternal truths into local regularities, patterns that hold within our cosmic neighborhood, but that have no claim to necessity outside it. And it raises a question that physics by itself may not be able to answer. Is there any fact of the matter about which laws are the real laws? Is there a level of description at which the contingency stops, at which there are truly necessary features of any possible reality? Or does the contingency go all the way down into a realm where not just the constants, but the very forms of the laws, the very existence of mathematical structure, are themselves without necessity? That question opens a door that physics cannot close because it is not a physics question. It is something deeper, and standing in the doorway, looking into what lies beyond it, is one of the most vertiginous experiences that thought can produce. Let's bring this back to Earth for a moment because there is a very concrete and very recent experimental context that deserves attention, one that does not require extra dimensions or multiverses to be deeply disturbing. In 2022, the Nobel Prize in Physics was awarded to Alain Aspect, John Clauser, and Anton Zeilinger for their experimental work on quantum entanglement and Bell inequality violations. The prize was given not just for a technical achievement, but for the confirmation of something profoundly important about the nature of reality. John Bell had shown mathematically in 1964 that any theory in which particles have definite properties prior to measurement, what are called hidden variable theories, must satisfy certain statistical inequalities. If those inequalities are violated experimentally, it means that the particles do not have definite properties prior to measurement. The Nobel laureates' experiments confirmed, with increasing precision and decreasing loopholes, that Bell's inequalities are violated. What this means is that quantum mechanics' picture of reality, in which particles do not have definite properties prior to measurement, is correct, and any picture in which they do is ruled out. This seems like a confirmation of quantum mechanics, which it is, but it is simultaneously a statement about reality that is deeply unsettling. The properties of particles are not determined until they are measured. Before the measurement, there is no fact of the matter about whether the particle is spin up or spin down. Not unknown, not hidden, not existing in a way we cannot access. Simply not determined. The universe is, at its fundamental level, indefinite, and definiteness is created by the act of observation. Now, if the fundamental building blocks of reality are indefinite prior to observation, and if observation is required to make them definite, then what is doing the observing? And when does observation happen? This is the measurement problem of quantum mechanics, and it is not a solved problem. It is one of the deepest open questions in physics and philosophy of science. In the Copenhagen interpretation, the measurement is performed by a classical apparatus, and the quantum system transitions from indefinite to definite when it interacts with this classical apparatus. But the Copenhagen interpretation gives no account of why some things count as classical apparatuses and others do not, where the boundary between the quantum and classical worlds lies, or why the act of measurement causes the wave function to collapse rather than simply evolving in a superposition. In the many worlds interpretation, the measurement does not cause a collapse. Instead, the universe branches, and every outcome occurs in a different branch. In this picture, every time a quantum measurement is made anywhere in the universe splits. Repeatedly, incessantly, at every quantum interaction, which is to say continuously, at every scale, from the quantum fluctuations driving the evaporation of black holes to the quantum transitions in atoms in your body. The universe you experience is one infinitely thin slice of an incomprehensibly vast branching structure, and the reality you call the world is no more complete a description of what exists than one page of a book is a complete description of the book. These are not comfortable thoughts. They are not meant to be. They are the natural conclusion of following quantum mechanics to its logical end. There is another way to think about the measurement problem that makes it even more personal and even more disturbing. The observer effect in quantum mechanics is not about consciousness technically. Most physicists are careful to say this. It is about physical interaction, about entanglement between the measuring device and the measured system, about the acquisition of information in a physical sense. But there is a line of argument, pursued seriously by some physicists and philosophers, that the role of information and observation in quantum mechanics points toward a conception of reality in which the physical world and the information processing systems within it are not as cleanly separable as we would like. John Archibald Wheeler, one of the most creative and influential physicists of the 20th century, coined the phrase "it from bit," suggesting that the physical universe, the it, might ultimately be derived from information, from binary choices, from bits. In Wheeler's picture, every quantum measurement is a yes or no question put to nature, and the physical universe is in some sense built up from the answers to these questions. This is a radical idea, and Wheeler was careful to present it as speculation rather than established physics. But the speculation is not idle. It connects with the holographic principle, with the AD-CFT correspondence, with the emerging field of quantum information theory, and with a growing body of work suggesting that the relationship between information and physical reality may be far more intimate than the classical picture suggests. If the universe is, in some deep sense, made of information, then the question "what is real?" is not entirely separable from the question "what is known?" And that boundary between physics and epistemology, between the study of the world and the study of how we know the world, begins to feel very thin indeed. Imagine you are standing in a building that you have always believed to be made of stone. Solid, impermeable, permanent stone. You have lived in it your entire life. You have never questioned the material. And then one day you press your hand against the wall, and you feel, just faintly, just at the edge of sensation, a slight give, a flexibility that stone should not have. You press harder, and the wall deforms slightly, and then springs back. Still looks like stone, still sounds like stone when you knock on it, but it is not behaving the way stone behaves. And once you have felt that give, you cannot unfeel it. Every wall in every room now carries the question. This is where physics is right now. The laws, the framework, the architecture of our understanding of reality. It still mostly looks like stone. It still mostly behaves like stone. But there are places, specific, measurable, precise places, where you press your hand against it and feel the give. And the give is not going away. and you cannot pretend you did not feel it. The problem of quantum gravity is worth examining from a different angle, because it is not just a technical problem in theoretical physics. It is a philosophical statement about the nature of reality. General relativity tells us that space-time is a smooth, continuous four-dimensional manifold, that gravity is the curvature of this manifold, and that the manifold exists and evolves according to precise differential equations. Quantum mechanics tells us that all physical systems are, at bottom, quantum systems described by wave functions and subject to the uncertainty principle. If space-time is a physical system, which it must be if it interacts with matter and energy, then space-time itself must be subject to quantum mechanics. It must have quantum fluctuations. Its geometry must be uncertain in a quantum sense. At the Planck scale, which is about 10 to the power of negative 35 meters, or about 20 orders of magnitude smaller than a proton, these quantum fluctuations of space-time are expected to be so large that the very concept of a smooth, continuous geometry breaks down. Space-time at the Planck scale, according to our best theoretical expectations, is not a smooth fabric. It is a seething, turbulent foam of fluctuating geometry of quantum uncertainties in distance and duration so large that neither space nor time has any stable meaning. Below the Planck scale, there is no here and there. There is no before and after. The coordinates you use to navigate reality, the very framework of location and time that makes the idea of something happening somewhere at some time coherent, dissolves into quantum noise. This is not a prediction that has been confirmed experimentally, because we have no instruments that probe the Planck scale. But it is the unavoidable implication of our two best theories, neither of which we have any good reason to distrust. The bedrock of physical reality, the substrate on which all events occur, is, according to the best physics we have, not bedrock at all. It is a quantum froth. And the stability of the space-time in which you are currently sitting, reading these words, is a large-scale average of something that, at its foundations, has no stability at all. The concept of emergence is central to how physicists think about this, and it deserves careful attention because it is doing a great deal of work in contemporary physics, and its implications are far-reaching. An emergent property is one that arises from the collective behavior of many smaller components, but that is not present in any individual component and cannot be easily predicted from the properties of the components alone. Temperature is emergent. Individual molecules do not have a temperature, but a large collection of molecules does. Wetness is emergent. Individual water molecules are not wet. Consciousness might be emergent from neural activity, and space-time, according to some theories, might be emergent from quantum entanglement, from the way quantum systems share information with each other in ways that generate the geometric relationships we call space and the sequential structure we call time. If space-time is emergent, then asking what happens inside a black hole singularity, or what happened before the Big Bang, may be like asking what happens to the temperature of a single molecule. The question is well formed linguistically but physically incoherent, because the concept does not apply at those scales. The smooth, continuous space-time of general relativity simply does not exist at the scales where we expect quantum gravity effects to be dominant. It is a macroscopic pattern, a statistical average, an approximation that is extraordinarily accurate at human scales and breaks down completely at Planck scales. And if space and time are emergent approximations rather than fundamental features of reality, then every physical law that is formulated in terms of space and time is also an approximation, valid in a particular regime, potentially misleading outside it. This includes all of classical physics. It includes general relativity. It might even include the standard model of particle physics. There is a thought experiment that John Bell himself posed, which is worth considering here, because it cuts to the heart of what quantum mechanics is actually telling us about reality. Bell asked, in a paper written in 1981, about the status of the wave function. Is it a real physical object, something that actually exists in the world the way a field or a particle exists? Or is it merely a mathematical tool, a bookkeeping device that tracks our knowledge about a system without itself being physically real? This distinction between the epistemic interpretation, in which the wave function represents our knowledge, and the ontic interpretation, in which the wave function is a real physical entity, might seem technical, but it is actually a question about the nature of reality itself. If the wave function is merely epistemic, then the indeterminacy of quantum mechanics is not a feature of the world, but a feature of our knowledge, and there is a definite underlying reality that the wave function is pointing toward imperfectly. If the wave function is ontic, then the indeterminacy is real, and before a measurement there is genuinely no fact of the matter about the properties of the system. Bell's inequalities, and the experiments that confirmed their violation, rule out the simplest class of hidden variable theories, but they do not rule out all ontic hidden variable theories, nor do they definitively resolve the epistemic ontic distinction. More recent theoretical work, including theorems by Pusey, Barrett, and Rudolph in 2012, has put strong constraints on epistemic interpretations, suggesting that the wave function must be at least partly ontic. But the debate is not closed, and the fact that the most fundamental mathematical object in our most successful physical theory, the object from which all of quantum mechanics predictions are derived, still does not have an agreed-upon interpretation after a century of use, is one of the strangest and most underappreciated facts in the history of science. Let's talk about the standard model of particle physics because it is frequently described as one of the greatest intellectual achievements in human history, and it is, and yet it is also a theory that its creators know to be incomplete in ways that are both obvious and deeply troubling. The Standard Model is a quantum field theory that describes three of the four fundamental forces: electromagnetism, the weak nuclear force, and the strong nuclear force, and all of the known elementary particles in terms of quantized fields and their interactions. It predicted the existence of the Higgs boson in 1964, and the Higgs boson was discovered at the Large Hadron Collider in 2012, exactly where the theory said it would be. The Standard Model has made predictions accurate to more decimal places than any other theory in science. It is, by any measure, spectacularly successful, and yet it does not include gravity. It does not explain why there are exactly 3 families of quarks and leptons. It does not explain why the masses of these particles have the values they do. It does not account for dark matter or dark energy. It does not explain the matter-antimatter asymmetry in the universe, the fact that the universe contains matter rather than equal amounts of matter and antimatter, which is what the Standard Model would predict. It does not explain why the strong force violates time reversal symmetry so extremely weakly, a puzzle called the strong CP problem, and it contains 19 free parameters, numbers, whose values must be measured and put in by hand, rather than derived from any deeper principle, numbers that include the masses of all the particles, the strengths of all the forces, and the parameters that govern the Higgs mechanism. A theory with 19 free parameters that cannot be derived from any underlying principle is not a fundamental theory. It is a very precisely fitted description of observations, enormously successful at prediction, but silent about its own foundations. And now the Large Hadron Collider at CERN, the most powerful particle accelerator ever built, the machine that was supposed to reveal the physics beyond the Standard Model, has returned a result that is in its own way the most unsettling result in the history of experimental particle physics, not because of what it found, but because of what it did not find. The LHC was designed with a range of energies that theory strongly suggested should be sufficient to reveal supersymmetric particles, the extra dimensions of string theory, or some other new physics that would point beyond the Standard Model. It found the Higgs boson, confirming the Standard Model's last major prediction, and then, after years of operation at its full design energy, it found nothing else. No supersymmetric particles, no extra dimensions, no new forces, no new particles of any kind that were not already predicted by the Standard Model. This absence has been called, with barely concealed despair by some physicists, a nightmare scenario, not because the LHC failed, but because it succeeded entirely, confirming the Standard Model completely, including in a regime where the Standard Model itself was expected to fail. The Standard Model cannot be the final word. It is internally inconsistent at high energies without new physics to stabilize the Higgs mass, a problem called the hierarchy problem, and yet the new physics that was supposed to stabilize it, primarily supersymmetry, was not found where it was most naturally expected to be. The machine that was supposed to open a door to a deeper level of reality found instead a wall. The hierarchy problem itself is worth examining closely because it reveals something important about how physicists think about the naturalness of the laws. The Higgs boson has a mass of about 125 GeV. In quantum field theory, The masses of particles receive corrections from quantum fluctuations, from the constant churning of virtual particles that contributes to every physical quantity. For most particles, these corrections are small compared to the particle's own mass. But for scalar particles like the Higgs, the corrections are enormous, proportional to the square of the highest energy scale in the theory, which is the Planck scale if there is no new physics between the electroweak scale and the Planck scale. Left to itself, the quantum corrections to the Higgs mass would drive it to values near the Planck scale, which is about 10 to the power of 18 GeV, enormously larger than its actual measured value. To get the Higgs mass to come out at 125 GeV, the bare mass of the Higgs and the quantum corrections must cancel each other to about 33 decimal places. 33 decimal places. This is the hierarchy problem. Not that the numbers do not work, they do work. You can always choose the parameters to make the calculation come out right. But that making it come out right requires a cancellation of extraordinary precision that seems to be demanding an explanation. Supersymmetry was the most popular proposed explanation because it provides a mechanism by which the corrections are automatically canceled by contributions from the supersymmetric partner particles, no fine-tuning required. Without supersymmetry, and with no new particles to provide a similar mechanism, we are left either accepting that the universe is extraordinarily fine-tuned at the 33 decimal place level for no apparent reason, or concluding that there is a deeper principle we are missing, one that makes the cancellation natural in a way we do not currently understand. And here is where you might be tempted to say that these are problems for physicists, technical problems in a technical field, and that they have no bearing on the everyday reality you experience. But that temptation deserves to be resisted, because the questions these problems raise are not just about particles and forces. They are about the nature of the description we are using, about whether the universe is the kind of place that has a true and final description, about whether the laws we have found are laws in the fullest sense or something more provisional and more fragile than we have assumed. And those questions do bear on everyday reality, not in the sense that your coffee will stop cooling or your car will stop obeying Newton's laws, but in the sense that the framework you use to interpret your experience, the implicit belief that reality is stable and rule-governed and ultimately knowable, is grounded in the success of physics. And if physics is less complete and less certain than you thought, then that grounding is less solid than you thought. The feeling that the universe makes sense, that it follows rules, that it can in principle be understood, is not a religious belief or a superstition. It is a conclusion that grew from the extraordinary success of the scientific project over 300 years. But that conclusion is only as strong as the science that supports it. And the science right now is sending mixed signals. Let's consider the nature of space itself, because there are things about space that we assume so automatically that it is difficult even to frame them as assumptions. You assume that space is three-dimensional. You assume that it is continuous, that there are no gaps in it, no minimum unit of distance below which the concept of distance loses meaning. You assume that it is the same in all directions, that there is no preferred direction of space. You assume that it is the same at all locations, that the geometry of space here is the same as the geometry of space there. These assumptions are called the isotropy and homogeneity of space, and they are foundational to modern cosmology. The standard cosmological model, the lambda CDM model, is built on the assumption that the universe is approximately uniform on large scales, that there is no special location, no center, no edge, just an expanding fabric of space with matter distributed roughly evenly throughout it. But the universe we actually observe has a large-scale structure, a cosmic web of filaments and voids that is statistically consistent with homogeneity, only on scales larger than about 1 billion light-years. Below that scale, the universe is decidedly not homogeneous, and there are hints, controversial hints, but hints that keep appearing in different data sets, that even on very large scales, larger than 1 billion light-years, there may be anomalies in the cosmic microwave background, alignments of the largest scale fluctuations that seem to prefer particular directions, a dipole modulation of the temperature of the CMB, a cold spot that is statistically unlikely within the standard model. None of these anomalies is individually definitive, but collectively, they suggest the possibility that the universe may have large-scale structure, preferred directions, or other departures from homogeneity at scales we have not yet fully characterized. And if the universe is not homogeneous on the largest scales, then the standard cosmological model is built on a foundation that may not be as secure as we assumed. There is a concept in physics called the cosmological principle, which is the assumption that the universe looks the same to all observers, that no location in the universe is special, that there is no center and no preferred direction. This principle is not derived from any fundamental law. It is assumed, partly for reasons of mathematical convenience, partly because it is consistent with the data we have, and partly because it aligns with a philosophical intuition that goes back to Copernicus, the idea that we do not occupy a special place in the universe, that wherever you are in the cosmos you see roughly the same thing. It is a compelling principle, aesthetically and philosophically, but it is an assumption, and like all assumptions it deserves periodic scrutiny. In 2020, a study published in the journal Astronomy and Astrophysics analyzed the distribution of radio galaxies across the sky and found an anomalously large dipole, a directionality in the distribution of galaxies that was significantly larger than what the cosmological principle would predict. The results suggested either that we are moving through space at a much higher velocity than previously thought, which would itself be surprising, or that the universe has a large-scale structure that violates the cosmological principle. The result was controversial and has been debated vigorously, but it has not gone away, and subsequent analyses have confirmed the anomaly's existence, while its interpretation remains contested. When one of the foundational assumptions of your cosmological model is showing cracks, it is worth asking what the model looks like without it. Now let's go back to something fundamental, something that feels so obvious that questioning it seems almost perverse, and that is the reliability of mathematics. As a description of physical reality, physics is mathematical. It always has been, and the mathematical nature of physics has been one of its greatest strengths. When mathematics and physical reality agree, the agreement is sometimes so precise, so unexpected, so beautiful, that it feels like more than coincidence. Eugene Wigner wrote a famous essay in 1960 called The Unreasonable Effectiveness of Mathematics in the Natural Sciences, in which he marveled at the fact that mathematics developed by pure mathematicians for entirely abstract reasons, with no thought of physical application, repeatedly turned out to perfectly describe physical phenomena discovered much later. Non-Euclidean geometry, developed in the 19th century as a purely abstract generalization of Euclidean geometry, turned out to be exactly the mathematical framework needed to describe the curved space-time of general relativity. Group theory, developed by mathematicians as an abstract study of symmetry, turned out to be the perfect language for describing the symmetries of particle physics. Complex numbers, which were originally regarded as an artificial trick to solve equations that had no real solutions, turned out to be fundamental to the structure of quantum mechanics. This effectiveness feels like it must mean something, like mathematics and physical reality are, at some deep level, the same thing, that the universe is, in some sense, mathematical in its nature. But there is a deeply unsettling alternative reading of this effectiveness, one that is less often discussed. Perhaps mathematics is unreasonably effective not because the universe is mathematical, but because our minds evolved to find patterns, to compress information, to build models that are predictive and internally consistent. Mathematics is the most refined and powerful form of model building that human cognition has produced. Of course, it is effective at describing the patterns we find in the universe. The universe has patterns, because if it did not, there would be no stable structures in it, no atoms, no stars, no planets, no biology, no beings capable of asking the question. The patterns that mathematics captures are real, but the mathematical structures we have built to describe them are our structures, our language, our compression of a reality that may be, at its deepest level, far more complex and far less neat than any mathematical description can fully capture. This is not a denial of physics. It is a reminder that maps are not territories, that the equations we write down are descriptions of reality, not reality itself, and that every description is an approximation, every model is a simplification, and every simplification leaves something out. The question that haunts physics right now is whether the things being left out are minor details, or whether they are the most important things of all. Let's think for a moment about what it would mean for the laws of physics to be emergent rather than fundamental. This is a distinction that physicists increasingly take seriously, and its implications are vast. A fundamental law is one that holds at all scales, in all regimes. with no exceptions, derived from nothing more basic. An emergent law is one that arises from more fundamental processes as a macroscopic approximation, valid in certain regimes but breaking down at others. Newton's laws of motion are emergent from statistical mechanics in the limit of large numbers of particles. Thermodynamics is emergent from the statistical behavior of many particles. Fluid dynamics is emergent from the behavior of many molecules. In each of these cases, the emergent laws are extraordinarily accurate and useful, but they break down at the scales of the underlying processes. If the laws of physics we have discovered, including general relativity and quantum field theory, are themselves emergent from some deeper level of reality, then they are not fundamental laws. They are effective theories, valid approximations in the regime we happen to inhabit, with a deeper reality beneath them that we have not yet accessed. This is actually how most physicists expect the story to go. The Standard Model is an effective field theory, valid up to some energy scale above which new physics takes over. General relativity is expected to break down at the Planck scale, where quantum gravity effects become important. The question is what lies beneath. What is the deeper level from which these effective theories emerge? And whatever it is, does it follow laws? Or does it simply be, in a way that generates the appearance of lawfulness at the scales we can see? There is a version of this question that goes all the way to the bottom and refuses to stop. Suppose you find the laws of quantum gravity, the theory that unifies general relativity and quantum mechanics and describes the behavior of spacetime at the Planck scale. Are those laws fundamental, or do they emerge from something deeper still? And if they emerge from something deeper, do those deeper laws emerge from something yet more fundamental? Is there a bottom, a level at which the laws simply are, with no further explanation, no deeper substrate? Leibniz asked, why is there something rather than nothing? And the question has never been answered to anyone's full satisfaction. Physics can tell you what rules the something follows. It cannot tell you why there are rules, or why the rules are these rules rather than some other rules, or why there is a universe at all in which rules apply rather than a void in which nothing exists and nothing can be asked. These are not questions that physics can in principle answer, because physics takes the existence of a world as its starting point. The deepest question, the question of why any laws exist at all, is prior to physics. It is prior to any possible empirical investigation. And standing at that depth, looking up at the entire edifice of human knowledge, you realize that every law, every equation, every experimental result, every confirmed prediction floats on an abyss that has no bottom. The laws of physics are not foundations. They are rafts on a sea of unknowing, very reliable rafts, very precisely crafted rafts, but rafts nonetheless. Now, you might think that this kind of philosophical reflection is all very well, but doesn't connect to the practical reality of physics as it is actually done. But the connection is more direct than you might think, because the questions being asked at the frontiers of theoretical physics right now are not merely technical, they are philosophical. They are questions about what kind of thing a physical law is, about what counts as an explanation, about what it means for a theory to be correct, about whether the universe is the kind of place that has a unique, correct description, or whether multiple incompatible descriptions might be simultaneously valid. The disagreement about quantum mechanics. Interpretations is a philosophical disagreement that has physical consequences. The debate about whether the multiverse is science or metaphysics is a philosophical debate about the nature of scientific explanation. The question of whether the constants of nature are necessary or contingent is a philosophical question that determines whether physics can ever be complete. These philosophical questions are not peripheral to physics. They are inside it, at its core, and the fact that physics has not resolved them, that they have been debated for a century without consensus, suggests that physics is not as settled and as secure as its public image suggests. Let's go somewhere that is even less charted, into the territory of what physics might look like if the framework changes fundamentally, if the next revolution is as profound as the relativistic and quantum revolutions of the early 20th century. When Einstein published Special Relativity in 1905, he was not making a small correction to Newtonian mechanics. He was replacing the conceptual foundations of space and time with something entirely different, something that made Newtonian mechanics an approximation valid only at low velocities. When quantum mechanics was formulated in the 1920s, it was not a modest extension of classical physics. It replaced the classical picture of particles with definite properties with a completely different picture of wave functions and probability amplitudes, a picture so different from classical physics that the founders of quantum mechanics spent decades arguing about what it meant. The next revolution, whatever it is, will likely be similarly radical. It will likely require abandoning some conceptual framework that currently seems so basic, so obviously correct, that it is almost invisible to us. It will likely make our current theories, general relativity, and quantum field theory, look the way Newtonian mechanics looks from the perspective of general relativity, a very accurate approximation valid in a restricted regime, but not the true description of what is actually going on, what might be sacrificed. Some possibilities are already being seriously explored. Locality, the principle that objects interact only through contact or through fields that propagate at finite speeds, has already been challenged by quantum entanglement, and some approaches to quantum gravity suggest that locality may need to be abandoned at a fundamental level. The concept of a space-time continuum, the idea that space and time form a smooth four-dimensional manifold, is expected to break down at the Planck scale, and several approaches to quantum gravity, including loop quantum gravity and causal set theory, suggest that space-time is discrete at the smallest scales, that there is a minimum unit of space and a minimum unit of time, below which the concepts simply do not apply. The concept of a fixed background space-time, the idea that there is a pre-existing arena in which physical events occur, is already abandoned in general relativity, where space-time is dynamical, but in quantum gravity, it may need to be abandoned even more radically, with space-time geometry itself becoming a quantum variable that fluctuates and superimposes. And perhaps most radically, some approaches suggest that time itself may not be fundamental, that the appearance of a temporal sequence of events may be emergent from an underlying description in which there is no time at all, a description in which all moments exist simultaneously, and the experience of time flowing is a consequence of the way information is distributed across an atemporal structure. The possibility that time is not fundamental is perhaps the most personally disorienting implication of quantum gravity research, and it has been explored most thoroughly in the context of the Wheeler-DeWitt equation, which is the quantum analog of general relativity, derived by applying the canonical quantization procedure to the Hamiltonian formulation of general relativity. The Wheeler-DeWitt equation is remarkable for several reasons, but the most remarkable thing about it is that it does not contain time. The equation, which describes the quantum state of the entire universe, has no time variable. It is a timeless equation describing a timeless quantum state. The universe, from this perspective, does not evolve in time. It simply is, in a superposition of all possible configurations, and what we experience as the flow of time is a consequence of the correlations between different subsystems within this timeless whole. This is not a fringe idea. It is a serious technical result from one of the most straightforward attempts to apply quantum mechanics to gravity, and it has been explored by physicists including Julian Barber, Carlo Rovelli, and many others. The implications are staggering. If time is not fundamental, then the universe does not have a history in the usual sense. There was no Big Bang in the sense of a beginning. There is no future in the sense of something that has not happened yet. There is only the quantum state of the universe, atemporal and immutable, and within it the appearance of time. The experience of past and future and causality and change is a kind of emergent story that certain subsystems tell about their relationships with other subsystems. This is the kind of idea that, when you first encounter it, seems like it cannot possibly be right, because it contradicts so directly and so completely the most basic feature of your experience. You are experiencing time right now. You remember yesterday. You anticipate tomorrow. Time is not an optional feature of your experience. It is its most fundamental texture. And yet, here is a serious physical theory derived from taking our best theories and applying them consistently, telling you that time is not a fundamental feature of the universe. Not that our current theory of time is incomplete and will be superseded by a better one, but that time, as a fundamental ingredient of reality, may not exist, that it is something we experience but not something that is there in the deep structure of things. This is a conclusion that many physicists are uncomfortable with and actively resist. It is also a conclusion that the equations, taken at face value, seem to support. and the tension between the two, between the undeniable vividness of temporal experience and the equations that describe a timeless universe, is one of the deepest and most productive tensions in contemporary physics and philosophy of mind. The philosopher David Chalmers has pointed out that there are two kinds of problems related to consciousness. The easy problems, which include explaining cognitive functions like perception, attention, memory, and behavior, are problems that can in principle be solved by neuroscience and cognitive science, by characterizing the mechanisms that produce these functions. The hard problem is explaining why any of this is accompanied by subjective experience, why there is something it is like to be a conscious being, why the information processing in your brain is accompanied by the sensation of redness when you see red, by the feeling of pain when you are hurt, by the experience of time passing. Chalmers calls this the hard problem because it is not clear that any amount of mechanistic explanation can bridge the gap between the physical processes in the brain and the subjective character of experience. The hard problem of consciousness is not a solved problem. It is one of the deepest puzzles in all of philosophy and cognitive science, and it connects to the physics we have been discussing in a way that is rarely made explicit. If the universe is fundamentally quantum, and if quantum mechanics assigns a central role to observation and measurement, and if the nature of observation is ultimately connected to the existence of conscious observers, then the hard problem of consciousness and the measurement problem of quantum mechanics are not separate problems. They are aspects of the same problem. They are both asking about the relationship between the physical world and the mind that observes it, and neither has a satisfying answer. There are physicists who have taken this connection seriously and followed it toward genuinely radical conclusions. Roger Penrose, one of the most creative and rigorous mathematical physicists of the 20th century, has proposed that consciousness is not simply a product of classical computation in the brain, but is connected to a quantum gravitational process at the level of microtubules within neurons, a process that involves the objective reduction of superpositions at the Planck scale, mediated by effects of quantum gravity that we do not yet understand. Penrose's theory, developed with the anesthesiologist Stuart Hameroff, is controversial and has not been confirmed experimentally, but the impulse behind it, the sense that consciousness cannot be fully explained by classical physics and may require quantum gravitational effects for its understanding, connects to a long tradition of thinking about the relationship between mind and matter that goes back to the founders of quantum mechanics. Heisenberg, Bohr, Pauli, von Neumann, they all wrestled with the question of what role the mind plays in the quantum description of reality, and none of them arrived at a fully satisfying answer. The question is still open, and it sits at the intersection of the two deepest mysteries in science, the nature of quantum mechanics and the nature of consciousness, each of which is mysterious in its own right, and whose relationship may be the key to understanding both. Let us consider for a moment what happens when you take the simulation hypothesis seriously as a physical proposal rather than a philosophical speculation. The simulation hypothesis, popularized by philosopher Nick Bostrom and more recently by physicists like James Gates and Sylvester James, proposes that physical reality as we experience it might be a computational simulation run on some substrate we have no access to, by some process or entity that exists outside our simulated reality. This idea is often dismissed as science fiction, but there are specific features of physics that, if you look at them with an open mind, are at least consistent with the idea that reality has a computational substrate. The universe is quantized at the smallest scales. Quantum mechanics assigns discrete states to physical systems, energy levels, spin values, discrete quantum numbers. The Planck length and Planck time define minimum units of space and time below which our current physics breaks down. The universe obeys exact mathematical laws even though there is no obvious reason why it should. There is a maximum speed, the speed of light, which looks like a maximum rate of information transfer. The universe contains a finite amount of information, bounded by the holographic bound, which relates the maximum information content of a region of space to the surface area of that region, rather than its volume. These features are not proof of simulation, not remotely, but they are consistent with the idea that reality is computational in character, and the simulation hypothesis cannot be dismissed as incoherent. It is a serious philosophical proposal that connects to real features of physics. James Gates, a physicist at Brown University, made a remarkable discovery in his work on string theory and supersymmetry that the mathematical structures he was working with contain, embedded within them, a class of error-correcting codes known as doubly even self-dual linear binary error-correcting codes. These are the same kinds of codes that are used in computer science to detect and correct errors in data transmission. Gates found them appearing spontaneously in the equations of fundamental physics, in the mathematical descriptions of the laws of nature, not put there deliberately, not arising from some ad hoc construction, but emerging naturally from the mathematical structure of the theory. Gates himself has been careful about what to conclude from this, pointing out that it might simply reflect deep mathematical structure rather than anything computational. But the discovery is striking, and it sits alongside other features of physics in a way that is difficult to entirely dismiss. The universe appears to enforce consistency, to correct errors, to maintain mathematical coherence at every scale and in every interaction. This is what error-correcting codes do. The appearance of these codes in the mathematics of physics is either a profound coincidence, a deep mathematical truth, or a hint of something about the nature of physical reality that we have not yet understood. But let's be careful here, because there is a danger in the simulation hypothesis, and in speculative ideas generally, of filling the gaps in our understanding with a story that feels complete, but is not actually explanatory. If the universe is a simulation, what is it simulated on? What are the laws of physics in the simulator? Are those laws more fundamental than ours? Can they be violated? And if they can, does that change what we mean by a physical law at all? The simulation hypothesis does not resolve the question of why there are laws. It pushes it back a level. If anything, it makes the question more acute because now you have two levels of physical reality, the simulated level and the simulator level, and you still need to explain why there are laws at either level and why those laws have the character they do. The simulation hypothesis is best understood not as an answer but as a way of reframing the question, of making vivid the possibility that the laws we experience are not the deepest laws, that there may be a substrate beneath them that we cannot access from within our simulated reality. Whether or not the simulation hypothesis is literally true, the reframing it provides is genuinely useful because it highlights the fact that our physical laws might be implementation-level facts about a particular realization of reality rather than necessary truths about all possible realities. There is another direction in which the story extends, one that is less speculative and more grounded in actual physics, and that is the direction of complexity and emergence at the macroscopic level. We have been mostly talking about the fundamental laws at the smallest scales and the largest scales, but there are also deep puzzles about the behavior of complex systems at intermediate scales, systems made of many interacting components, whose collective behavior produces phenomena that are not obviously predictable from the laws governing their components. Life is the most striking example. Living organisms are made of atoms that follow the laws of quantum mechanics and the laws of chemistry, which are themselves derived from quantum mechanics. And yet the behavior of a living cell, its ability to replicate, to metabolize, to respond to its environment, to maintain itself far from thermodynamic equilibrium, seems to involve a kind of organization that is not clearly explained by simply applying the laws of chemistry to the collection of molecules. Physicists like Paul Davies have argued that life exploits quantum effects in ways that are not yet fully understood, that the precision of certain biochemical processes, including the efficiency of photosynthesis and the mechanism of enzyme catalysis, may involve quantum coherence, the ability of quantum systems to maintain superpositions of states even in the warm, wet, noisy environment of a living cell. If this is right, then life is not just chemistry. It is quantum chemistry, and its behavior may involve features of quantum mechanics that are not captured by the classical approximations we usually use when describing biological systems. The field of quantum biology is young and controversial, but it has produced some genuinely remarkable results. The efficiency of photosynthesis, the process by which plants convert light into chemical energy, approaches the theoretical limit of efficiency in a way that seems impossible if the energy is simply diffusing randomly through the molecular antenna until it reaches the reaction center. Experiments performed in the 2000s suggested that the energy might instead be propagating as a quantum wave exploring all possible paths simultaneously through the antenna complex. and finding the most efficient path, the way a quantum particle finds its path in quantum mechanics. This result was initially very exciting and seemed to confirm the role of quantum coherence in biological systems. Subsequent work has complicated the picture, and the community is still debating the extent to which genuine quantum coherence, as opposed to classical wave-like effects, plays a role in photosynthesis. But the fact that the question is open, that biological systems may be operating at the quantum classical boundary in ways that are not fully understood, suggests that the relationship between the laws of quantum mechanics and the laws of biology is not as simple or as clean as was once assumed. And then there is the matter of the human brain, which brings us back to consciousness by a different route. The brain is a physical object made of neurons, connected by synapses, powered by electrochemical gradients operating by the same physical laws as everything else. Its behavior is in principle describable by physics, but the brain also generates consciousness, subjective experience, the sense of being a self with a perspective, memories, intentions, the experience of the present moment. And consciousness, as we have noted, is not explained by the current laws of physics. It is not part of the standard model. It is not a consequence of general relativity. It is not accounted for in any fundamental physical theory, not as a necessary consequence, not as an emergent property whose emergence is understood, but as something that exists in the universe and is produced by certain physical systems and whose relationship to the physical laws we know is genuinely, deeply, profoundly unclear. There are two ways to respond to this. One is to say that consciousness will eventually be explained by the physical laws we know, that it is just a very complex computational or information processing phenomenon and we simply haven't worked out the details yet. The other is to say that the fact that our current physical laws cannot account for consciousness is itself significant, that consciousness is a feature of reality that lies outside the scope of our current physics, and that a complete physical theory will need to incorporate it in a way that our current theories do not. Both responses are defensible, but the second one has a radical implication. If consciousness is not captured by the current laws of physics, then the current laws of physics are incomplete in a way that goes beyond not knowing about dark matter or not having a theory of quantum gravity. They are incomplete at the level of failing to account for the most intimate and immediate feature of your experience of being alive. Let's take stock of where we are, because the accumulation of what we have covered deserves a moment of reflection. We have a quantum mechanics that is extraordinarily successful but whose meaning is unknown. We have a general relativity that is extraordinarily successful but is incompatible with quantum mechanics. We have a universe that is 95% composed of things, dark matter and dark energy, that we cannot characterize within our current framework. We have a standard model that is extraordinarily successful but has 19 free parameters and cannot explain gravity, dark matter, dark energy, or the matter-antimatter asymmetry. We have a cosmological constant that is fine-tuned to 120 decimal places without explanation. We have a Higgs mass that is fine-tuned to 33 decimal places without explanation. We have a Hubble tension that has persisted for over a decade and shows no sign of resolving. We have Bell inequality violations that rule out local realism, the assumption that particles have definite properties independent of measurement, and that suggests the universe at its most fundamental level is non-local in a way we do not fully understand. We have a hard problem of consciousness that our physical theories cannot address. We have an arrow of time that is not explained by the fundamental laws. We have a measurement problem that has been debated for a century without resolution. And we have a mathematical framework that is extraordinarily successful in the regime we contest, but which we know is not fundamental, and whose deeper foundations remain entirely unknown. This is the state of physics in the 21st century. Not a nearly complete science making final refinements. A deeply successful descriptive enterprise built on conceptual foundations that are, on inspection, far less solid than they appear. Now, one of the most important things to say at this point is that none of what we have described means that physics is wrong, in the sense that the laws we have discovered are going to stop working tomorrow. Your phone's GPS will still compensate correctly for relativistic time dilation. The semiconductor transistors in your computer will still behave as quantum mechanics predicts. The structural calculations in a bridge will still follow Newtonian mechanics with all the precision that is needed. The effective laws, the practical descriptions, the engineering level physics, all of that is secure. What is not secure is the interpretation, the philosophical foundation, the claim that the laws we have are the ultimate laws, that the framework is complete, or nearly complete, that we understand what reality actually is at its deepest level. The distinction between these equations work, and we understand what is really going on, is crucial, and it is a distinction that public communication of science often blurs. Physics has given us unparalleled power to predict and control phenomena. Physics has not given us a clear, agreed-upon picture of what reality actually is. Those are two different achievements, and we have been more successful at the first than at the second. The philosopher of science Thomas Kuhn wrote in his 1962 book, The Structure of Scientific Revolutions, about the concept of a paradigm, a framework of assumptions, methods, and concepts that defines what counts as a legitimate scientific question and a legitimate scientific answer within a given field at a given time. Normal science, in Kuhn's account, is the process of working within a paradigm, solving problems that the paradigm defines as soluble, extending the paradigm's range of application, filling in the details of the picture the paradigm provides. Revolutionary science is what happens when the accumulation of anomalies, results that the paradigm cannot explain, reaches a point where a new paradigm is needed, a new framework that resolves the anomalies and opens up new questions that the old paradigm could not even formulate. The shift from Newtonian to relativistic physics was a paradigm shift. The shift from classical to quantum physics was a paradigm shift. Both shifts preserved the practical success of the older framework, which became an approximation valid in certain regimes, but both shifts completely transformed the conceptual picture of what reality is. Looking at the current state of physics, with its multiple deep anomalies, its incompatible theories, its unresolved foundational questions, its 30 years of failed attempts to find physics beyond the standard model, the question of whether we are living through the early stages of the next great paradigm shift is not merely rhetorical. It is a genuine scientific and historical question, and the answer, based on the evidence, seems to be possibly yes. What would the next paradigm look like? This is inherently speculative, but the speculation is grounded in the direction the anomalies seem to be pointing. The next paradigm might involve a fundamental reconception of space-time, replacing the continuous smooth manifold of general relativity with a discrete or network structure from which smooth space-time emerges at large scales. It might involve a fundamental role for information, with the geometry of space emerging from quantum entanglement and the flow of information between subsystems. It might involve the abandonment of locality as a fundamental principle, with some form of non-local connection being a primitive feature of the underlying theory. It might involve a reconception of what physical law means, acknowledging that the laws we observe are emergent regularities of a particular cosmic epoch or region, rather than eternal necessary truths. It might involve, most radically, a reconception of the relationship between the physical world and the minds that observe it, acknowledging that this relationship is not as clean as the classical picture assumed. Whatever form it takes, the next paradigm will almost certainly retain all the practical successes of the current one. General relativity and quantum mechanics will become approximations of something deeper. The way Newtonian mechanics became an approximation, the effective laws will not break, but the story we tell about what they mean, about what they are describing, about what reality actually is, will change. And that change will be as profound and as disorienting as any change in our understanding of the world has ever been. There is a specific and quite recent development in physics that deserves attention in this context because it represents a possible bridge between quantum information theory and space-time geometry, a bridge that, if it holds, could be the first step toward the next paradigm. The development is the conjecture by Juan Maldacena, known as the ER equals EPR conjecture, which he proposed with Leonard Susskind in 2013. The conjecture states that quantum entanglement, specifically the EPR correlations between entangled particles that Einstein called spooky action at a distance, is equivalent to a wormhole, specifically an Einstein-Rosen bridge, a tunnel through spacetime that connects two distant regions, ER equals EPR, where ER refers to Einstein-Rosen bridges and EPR refers to Einstein, Podolsky, and Rosen, the authors of the famous 1935 paper about quantum entanglement. The conjecture says that entanglement and geometry are, in some deep sense, the same thing, that the non-local correlations between entangled particles correspond to geometric connections through spacetime, and that spacetime connectivity is built up from quantum entanglement. This is a remarkable and deeply counterintuitive proposal, and it has not been proven, but it connects naturally with the holographic principle, with the firewall paradox, and with the general idea that spacetime is emergent from quantum information. If true, it means that every time two particles become entangled, they are in some sense geometrically connected through a microscopic wormhole. The fabric of spacetime is woven from entanglement. Space is not the background on which physics happens. Space is made of physics. The implications of this idea extend far beyond the technical details of quantum gravity. If space is made of entanglement, then the connectivity of space, the fact that here and there are separated by a distance, is a consequence of the pattern of entanglement in the underlying quantum state. Regions that are highly entangled are close together in space. Regions that are weakly entangled are far apart, and a region from which entanglement is removed would, in this picture, disconnect from the rest of space, become spatially isolated in a way that is more fundamental than mere physical distance. The physicist Mark van Ramsdonk showed explicitly, in a 2010 paper, that if you take a maximally entangled quantum state and gradually reduce the entanglement, the corresponding spacetime geometry in the higher dimensional description becomes thinner and eventually disconnects into two separate pieces. Entanglement holds space together. Remove the entanglement and space tiers. This is a concrete mathematical result, not a metaphor, and its implications for what space actually is are difficult to overstate. Space, the thing you are sitting in right now, the thing that separates you from the walls, the thing that contains all the objects you have ever encountered, is not a fixed background. It is a pattern of quantum correlations. It is, in some sense, made of relationships between quantum systems. And those relationships, in principle, could be different. Space could be different. The geometry of reality is not given. It is built. And what it is built from is something so strange, so counterintuitive, so far removed from the common sense notion of an object sitting in a space, that the very language we use to describe it begins to strain at the seams. Let's think about what this means for causality one more time, because causality is the backbone of our intuitive understanding of how things work, and the picture we are approaching from multiple directions suggests that causality, like space and time, may be emergent rather than fundamental. In a universe where space-time is emergent from quantum entanglement, causal relations are also emergent. There is no fundamental before and after at the level of the underlying quantum state. Causality arises as a large-scale pattern in the emergent spacetime, the same way temperature arises as a large-scale pattern from the motions of molecules. And just as temperature breaks down at the scale of individual molecules, causality breaks down at the scale of the underlying quantum substrate. This means that at the deepest level of reality, the question, what caused this, may not have a well-formed answer. Causation may be as emergent as temperature, as approximate as Newtonian mechanics, as valid in certain regimes as a smooth space-time geometry. And if causality is emergent, then the entire structure of scientific explanation, which is built on the identification of causes and effects, is also emergent, valid in the regime where space-time is a good approximation, potentially unreliable or meaningless at the level of the fundamental theory. You might be wondering at this point whether any of this has been confirmed, whether experiments have actually found violations of causality, breakdowns of space-time, evidence of the quantum structure of space. And the honest answer is, not directly, not yet. The scales at which these effects are expected to be significant are far beyond what current technology can reach. The Planck scale is 20 orders of magnitude smaller than a proton, and even the LHC, which accelerates particles to energies 1 trillion times greater than their rest mass energies, is still 15 orders of magnitude away from Planck scale energies. Direct experimental access to Planck scale physics is not something we should expect in the near term, or possibly ever, given the energy scales involved. But this does not mean that quantum gravity is entirely beyond observational reach. Subtle effects might be observable at lower energies, in the polarization of light from gamma-ray bursts, in the statistics of cosmic ray showers, in precision tests of Lorentz invariance, the symmetry of spacetime under boosts and rotations that is fundamental to both special relativity and the Standard Model. So far, These tests have not found deviations from the standard physics, but they have set increasingly tight upper limits on the size of quantum gravity effects, limits that are beginning to constrain the available theoretical space for viable quantum gravity theories. And here is something that deepens the mystery further: the fact that we can observe the universe at all, that we can measure the cosmic microwave background, that we can detect gravitational waves, that we can study particle physics at the LHC, depends on the universe being transparent and regular and lawful enough to allow instruments to work, signals to propagate, and measurements to be made. But the very success of our instruments, the very fact that physics works well enough to build telescopes and colliders and interferometers, might be precisely what prevents us from seeing the deeper level at which it breaks down. We are inside the system we are trying to study. We are made of the same matter and energy and space-time that we are trying to understand. Our instruments are built from the same quantum fields whose behavior we are trying to probe. And there is a deep epistemological limit here that is not merely practical but potentially fundamental. A system cannot fully describe itself from within. The map cannot contain a complete description of itself. A brain cannot fully model its own operation. And a universe cannot, from within, generate a complete description of all its own laws, because any description it generates is itself part of the universe, and therefore part of what needs to be described. This is not a new observation. Kurt Gödel proved something analogous about formal mathematical systems in 1931, showing that any sufficiently powerful axiomatic system contains true statements that cannot be proven within that system. The universe of physics may have an analogous incompleteness, a set of truths about its own nature that cannot be accessed from within it, no matter how sophisticated the instruments or how powerful the mathematics. Gödel's incompleteness theorems deserve a moment of careful attention here, because they are often invoked loosely and deserve to be understood precisely, and because their implications for physics are genuinely significant. Gödel showed that any formal system that is powerful enough to express basic arithmetic is either incomplete, meaning there are true statements within it that cannot be proven from its axioms, or inconsistent, meaning it can prove contradictions. You cannot have a formal system that is both powerful enough to do interesting mathematics and also complete and consistent. This result was devastating for the program of David Hilbert, who had hoped to place all of mathematics on a secure, complete, and consistent axiomatic foundation. Hilbert's program was shown to be impossible in principle, not just difficult. Now, physics is not the same as mathematics. Physical laws are not axioms in a formal system, but the analogy is suggestive. If the mathematical framework that underlies physics is subject to Gödelian incompleteness, then there may be physical truths that cannot in principle be derived from any finite set of physical laws, no matter how powerful and how complete our theories become. The universe may be, in a precise mathematical sense, inexhaustible. There may always be more to know, and some of what there is to know may be knowable only from outside the framework we are currently using, from a vantage point that we cannot currently occupy. There is a physicist named David Deutsch who has argued against this kind of pessimism, that knowledge is in principle unlimited, that the laws of physics permit the construction of a universal computer, and that a universal computer can in principle simulate any physical process, including the process of scientific discovery itself. Deutsch's view is optimistic and rigorous and connected to his work on quantum computation. The idea that quantum computers can in principle solve problems that classical computers cannot, not just faster but qualitatively differently. Quantum computation is one of the most exciting frontiers of current physics and technology, and it connects directly to the foundations we have been discussing. Because quantum computers work by exploiting superposition and entanglement, the very features of quantum mechanics that are most counterintuitive and most philosophically puzzling, to perform computations that no classical device could perform in any reasonable time. The fact that these strange features of quantum mechanics can be harnessed for computation is itself a remarkable statement about the physical nature of information. Information, in a quantum universe, is not classical. It is quantum, and the computational power available in a universe governed by quantum mechanics is incomparably greater than what is available in a classical universe. This makes the universe, in some sense, more powerful than we thought, but it does not make it more comprehensible. A universe that is computationally More powerful is not necessarily a universe that is more transparent to understanding. Let's go to the very edge of what is currently being said seriously in physics, to a place where the language begins to break down and the concepts strain against their own limits. There's a growing body of work, associated with physicists and philosophers including Sean Carroll, David Wallace, Carlo Rovelli, Lee Smolin, and others, that takes seriously the question of whether physical laws are real in the sense of being features of the universe, or whether they are descriptions that exist in minds, patterns that intelligent observers project onto a universe that is, at bottom, just things happening without any compulsion to follow rules. This is not nihilism about science. It is a serious philosophical position, sometimes called relationalism or structural realism, that attempts to say what is real in physics without committing to the existence of laws as platonic objects floating outside the universe. In this view, what is real is not the laws themselves, but the relationships between physical systems, the patterns of correlation and interaction that we describe using mathematical laws, but that exist independently of the description. The laws are our language, the relationships are the reality, and the question of whether the laws could be different is, in this view, not a question about the universe, but a question about which language is most useful for describing it. Carlo Rovelli, in his work on relational quantum mechanics, has pushed this idea furthest in the quantum domain. In Rovelli's interpretation, quantum mechanics is not a theory about what the world is, but about what physical systems know about each other, about the information that one physical system has regarding another through their physical interactions. The wave function is not a description of an objective state of the world. It is a description of the information one system has about another, and the collapse of the wave function upon measurement is not a physical event that happens to the measured system. It is an update in the information state of the measuring system, the same kind of update that happens when you learn something new and revise your beliefs. In this picture, there is no single objective quantum state of the universe. There are only relative states, descriptions of how each system appears to every other system that has interacted with it. Reality, in Rovelli's picture, is not a collection of objects with properties. It is a web of interactions, a network of mutual descriptions, each local and partial and perspectival. There is no view from nowhere, no God's eye perspective from which the true state of the universe can be read off. Every description is someone's description, made from somewhere, valid for certain purposes, and necessarily incomplete. This is not merely a philosophical position. It has physical content. Relational quantum mechanics makes specific predictions about the structure of quantum correlations that differ from some other interpretations, and that might, in principle, be tested. More importantly, it suggests a picture of physics that is fundamentally different from the classical picture, in which reality consists of objects with definite properties existing in a fixed space-time background. In the relational picture, the fixed space-time background is gone. The definite properties are gone. What remains is the pattern of interactions, the web of physical relationships, from which space-time and properties and everything else that we call real emerges as a large-scale description that is valid in certain regimes and breaks down in others. This is not the end of physics. It is, potentially, the beginning of a deeper physics, a physics that takes seriously the relational, perspectival, information-theoretic character of quantum mechanics and builds a new framework on that foundation, rather than trying to recover a classical picture from quantum mechanics by forcing it into frameworks it was never designed to inhabit. And now, we are approaching the place where the words begin to fail, not because the physics becomes too technical to explain in ordinary language, but because we are reaching the edge of what ordinary language was built to describe. Language evolved to communicate about objects and actions in a three-dimensional world unfolding in time. It has concepts for things, for properties, for causes, and effects for before and after. It was not built to describe a reality in which there are no fundamental things, no intrinsic properties, no fundamental causality, no fundamental time. When physicists try to describe quantum gravity, or the emergence of space-time from entanglement, or the relational nature of quantum states, they run into the limits of language, not because they are being imprecise, but because the concepts that ordinary language provides are the wrong concepts for the job. The sentence "is space-time emerged from quantum entanglement" uses words, space, time, quantum, entanglement, that carry meaning from the regimes where they were defined, and it asks them to describe something that may be prior to those regimes, prior to the concepts themselves. It is like trying to describe color to someone who has never seen, using only the vocabulary of sound. You can make analogies, you can gesture toward what you mean, but the description is necessarily partial, necessarily distorted by the medium through which it passes. This linguistic limitation is not unique to physics. It is a feature of all attempts to describe reality at levels beyond ordinary human experience, whether that means the very small, the very large, the very fast, the very early, or the very deep. But it becomes particularly acute when the level being described is the level at which the concepts used to describe all other levels break down, when space and time are themselves the things being explained rather than the background against which explanation occurs. The entire framework of description is under pressure, and this pressure is itself informative. It tells you that you have reached the edge of the regime in which your concepts are reliable. It tells you that you are at the boundary between what can be said and what can only be pointed toward. And pointing toward things that cannot quite be said is, paradoxically, one of the most important things that physics can do right. Now, because it maps the shape of the unknown, it traces the outline of the gap between what we can describe and what we need to describe, and that outline is the most precise statement currently available of what the next step needs to accomplish. So here we are. You have traveled from the comfortable certainty of high school physics, of falling apples and orbiting planets and predictable collisions, through the strangeness of quantum mechanics and the power of general relativity, into the deep uncertainty of quantum gravity and the philosophical abyss of the measurement problem and the hard problem of consciousness and the emergent nature of time and space. You have seen a universe that is 95% unknown, governed by laws that are incompatible with each other at their limits, built on a space-time that may not be fundamental, populated by particles whose properties do not exist prior to measurement, threaded through with non-local correlations that violate our deepest intuitions, about locality and causality, expanding at an accelerating rate driven by an unknown force, held together by an unknown substance, and described by a mathematical framework that produces the right answers. In the regime we can test but fails catastrophically when pushed to its limits, you have seen the cracks in the foundation, the tensions in the data, the incompleteness of the theories, the unresolved debates about meaning and interpretation, and you might be thinking, this is disturbing. You would be right. It is disturbing, but it is the right kind of disturbance. Because here is what the history of science teaches, over and over, in case after case, revolution after revolution. The moments that felt like the ground falling away were the moments when something true and important was about to be understood for the first time. When Copernicus removed the Earth from the center of the universe, it felt like a catastrophe to the worldview that had placed humanity at the center of creation. When Darwin showed that humans were continuous with the rest of the animal kingdom, shaped by the same blind forces of variation and selection, it felt like a diminishment of something precious. When Freud suggested that much of mental life is unconscious, not accessible to the rational self we identify with, it felt like a violation of the self's sovereignty over its own mind. Each of these shifts was disorienting. Each of them eventually produced a deeper and more accurate understanding of the world, and each of them required giving up a comfortable certainty in exchange for a more demanding truth. The current situation in physics is asking for the same exchange. It is asking you to give up the comfortable certainty that physics has the answers, that the laws are stable and complete and universal, and fundamentally understood, in exchange for something more honest. The recognition that we are at a moment of profound transition, that the map we have been using is extraordinarily good but not complete, and that the territory it describes is stranger and more interesting than the map suggests. But do not mistake this for relativism, for the idea that all descriptions are equally valid, that the laws of physics are arbitrary, that science is just one story among many with no special claim to truth. That would be the wrong lesson, and it would betray the extraordinary achievement that physics represents. The laws we have discovered are real. They describe real patterns in the world. They work. The double helix is real. The electron is real. The curvature of space-time around massive objects is real. Gravitational waves are real. The Higgs field is real. These are genuine discoveries about the structure of the universe, verified by experiments so precise and so reproducible that dismissing them would require a level of skepticism that consumes itself. The laws of physics are not failing in the sense that they are being shown to be wrong. They are failing in the sense that they are being shown to be incomplete, which is an entirely different thing. Incomplete is not wrong. Incomplete is human. Incomplete is, in fact, the condition of all knowledge at all times in all domains. The laws of physics being incomplete does not make them unreliable in the regime where we have tested them. It makes them reliable in that regime and uncertain beyond it. And the boundary of the regime, the precise location where reliability becomes uncertainty, is the most scientifically important address in the universe. There is something profound and almost sacred about that boundary, that edge where the known meets the unknown, where the equations still work but their meaning is unclear, where the data is clean but the interpretation is contested, where the framework is intact but its foundations are uncertain. That boundary is where physics lives right now, at its most alive and most productive and most genuinely uncertain moment. It is where the next Newton or the next Einstein will make their mark, not by solving a problem within the existing framework, but by finding a new framework that makes the problems dissolve, that reveals them to have been artifacts of the old way of thinking, rather than features of reality itself. That person, or those people, may be alive right now. They may be a graduate student working on a problem that seems purely technical, following a thread of mathematics that will turn out to lead somewhere no one has looked before. They may be a philosopher asking a question that physicists have dismissed as too vague to be useful, a question that will turn out to be the key to a deeper description of reality. They may be an experimentalist designing an instrument that will measure something in a new way, a way that reveals a discrepancy that reshapes the entire field. The next revolution is coming. We do not know what form it will take. We do not know when it will arrive. But the signs that it is needed are clear, and they are accumulating. And in the meantime, you are here. You are a conscious being, made of atoms that follow quantum mechanical laws, sitting in a curved space-time generated by the distribution of matter and energy in the universe, experiencing a flow of time that the fundamental equations say is not fundamental, perceiving a three-dimensional space that may be emergent from quantum entanglement, measuring and observing a world whose properties may not exist prior to the act of measurement, asking questions about the nature of reality using a mind whose relationship to the physical processes that produce it is one of the deepest unsolved problems in science. You are, in a very real sense, the universe observing itself, the cosmos generating a local pocket of self-awareness and turning that awareness back on the whole. And what the awareness finds, when it looks closely and honestly at the laws it has discovered, is that those laws are magnificent and precise and extraordinarily productive and also incomplete, and also possibly emergent, and also possibly local rather than universal, and also possibly not the final word, not even close to the final word. So the next time someone tells you that physics has explained everything important, that the laws of nature are known and the remaining work is just filling in the details, you will know better. You will know that the two most successful theories in the history of physics cannot be reconciled with each other. You will know that 95% of the universe is made of things we cannot characterize. You will know that the cosmological constant is wrong by 120 orders of magnitude. You will know that the arrow of time is unexplained. You will know that the measurement problem is unresolved. You will know that the meaning of quantum mechanics is unknown. You will know that the Hubble tension is real and growing. You will know that supersymmetry has not been found where it was expected. You will know that the hard problem of consciousness lies entirely outside the current physical framework, and you will know that the space-time you are sitting in may be an emergent approximation built from quantum entanglement, that time may not be fundamental, that causality may be a large-scale pattern rather than a deep truth, and that the laws of physics themselves may be contingent features of this particular region and epoch of the cosmos, rather than eternal necessary truths about all possible reality. You will know all of this, and you will hold it not as despair, but as the most honest and the most exciting description of where we are. Because here is the thing that never changes. Even as everything else is called into question, the questions are real. The mystery is real. The universe is out there, doing whatever it is doing, being whatever it is being, following whatever structure it has at its deepest level. And we are here, trying to understand it, with the limited instruments of our senses and our mathematics and our language and our minds. And the gap between what we are trying to understand and what we currently understand is not a sign of failure. It is the engine of the entire enterprise. It is what makes the next experiment worth running, the next equation worth writing, the next question worth asking. The laws of physics were supposed to be the final answer to the question of how the universe works. What they have turned out to be is the best current chapter in a story that is far longer and far stranger than anyone expected. And the next chapter, the one that resolves the tensions and transcends the incompatibilities, and reveals the deeper structure from which space and time and matter and law all emerge, that chapter has not been written yet. It might be the most important chapter in the history of human thought, and it begins exactly here, at the precise moment when the ground starts to feel uncertain beneath your feet, when the laws start to feel less like stone and more like something that can give, when the certainty that physics promised starts to feel like the comfortable story we told ourselves before we were ready to know the truth. The laws of physics did not simply fail. They revealed their limits. And the limits of our laws are the map of what we do not yet know. And what we do not yet know is the most important thing in the world. Because somewhere inside that unknown, at the depth where the equations break and the words fail and the intuitions dissolve, there is something real. Something that is there whether we describe it correctly or not. Something that was there before the first equation was written and will be there after the last one is. Something that the universe is doing right now. At every scale, from the Planck length to the cosmic horizon, in every quantum fluctuation, in every entangled particle, in every gravitational wave propagating across the fabric of space-time, in every photon that has been traveling since before the first star ignited, that something is not waiting for us to understand it. It is not holding still. It is not behaving the way the textbooks say it should, or at least not only that way, not at all scales, not in all regimes, not with the completeness and the certainty that we have, until quite recently, been comfortable assuming. And that small, persistent, irresolvable gap between what we assumed and what is actually out there, that is not a problem to be solved and put away. That is the thing itself. That is the frontier. That is the place where, if you are paying attention, you can feel the whole edifice of human knowledge pressing up against something it has not yet learned to describe. Something that, if you listen very carefully, you might almost hear. Not an answer. Not yet. Not quite. Something older and stranger than an answer. The sound of a question that has not yet been asked.